So today we're very happy to have Michael Hutchings here, who will tell us about quantitative closing lemmas. And he's asked that people turn on their cameras so he can see and get feedback. So please do that if you are able to. And how would you like people to ask questions?
You can just jump right in um, to speak up.
Okay, yeah. So unmute yourself and just ask if you have questions. Okay, so go ahead.
Hey, thank you very much for the invitation. Um, so, yeah, I'm hoping to. You're all like learning about math research, right? Or writing papers. So, I'm hoping to give you at least a little bit of an idea of what research mathematicians do. So, I want to tell you about some of the more. I tried to pick like the most accessible thing that's in my recent research, and can also tell you a little bit about the process. So when I was your age, I had absolutely no idea what mathematicians did. I thought they like computed more digits of pi and like made the tables of integrals that are in the back of a calculus book, and that sounded pretty boring. Um, so I didn't really want to be a mathematician at that point. But later I learned how cool it is. So, and I'm sorry, I'm reusing slides from a previous talk. I have I'm I'm not very technical skilled, so it would have taken me a lot of time to change where it says math on tap to where it says Euler circle. Um, but the um, math on tap is where we give some talks about what we're working on to friends at the Berkeley Math Department. So that's fun too. Okay, so what am I going to be talking about? I'm going to be talking about dynamics. So in mathematics, dynamics is we are studying how some system evolves in time. Like there's a solar system. So there are the sun, a bunch of planets, a bunch of smaller objects, and they're all moving around according to the laws of gravity. And you can say, all right, well, what's going to happen in a long time? It's actually quite, it's kind of a miracle. Well, we wouldn't be here if it weren't true, but it's kind of a miracle that the solar system is relatively stable. You know, like each planet orbits around the sun. And if you just have like one sun and one planet, then that's very stable. It just repeats, just goes around in an ellipse over and over. Um, so each of the planets are doing that individually, but the planets are also pulling on each other a little bit, so that could sort of tweak their orbits. And you could worry, all right, what if we wait a billion years? Like, could some catastrophe happen? Like two planets collide that actually has happened in the past, or like a planet falls into the sun, or it gets actually ejected from the solar system and wanders alone in space for the rest of eternity, which is very sad. So why doesn't that happen? Well, I don't know. So I'm not going to get into that. But that's an example of a hard question you can talk about in dynamics. Um, but I'm going to talk about periodic orbits. So that's sort of the simplest aspect of a dynamical system. So periodic orbit is it means behavior is repeating in time. So you start with some state of your physical system, and after some amount of time, you come back to exactly the same state, and then you just repeat forever. So an example of this would be a single planet orbiting a star. So then it just goes around in an ellipse and repeats. Um, and if you have some more complicated dynamical system, what can we say about the periodic orbits? Like, do they exist? How many are there? What are their properties? So this is a subject of active mathematical research today. Um, now, the basic mathematical setup is Hamiltonian dynamics. So this is one way of describing classical mechanics. So in the simplest version, you have n position coordinates and n momentum coordinates. So denote the position coordinates by x1 through xn and the momentum coordinates by y1 through yn. So if you know all of those 2n variables, and that is the state of your system at some time, it tells you where you are and where you're going. Um, and then there's a function defined on this state space, the Hamiltonian. So for every state, there's a real number. And this represents the total energy of the system. And then the equations of motion are that well, if I think of x1 through yn as functions of t, so t is time, then the derivative of xi with respect to t is equal to the partial derivative of h with respect to yi. And the derivative of yi with respect to t is minus the partial derivative of h with respect to xi. I'll show you an example in a minute. So this is a system of ordinary differential equations. You have two n variables or two n functions of time, and these equations tell you the speed at which each of these variables is changing in time. And it's given in terms of the derivatives of h. That makes sense? Please feel free to jump in with questions about whatever. Like I have a bunch of slides. I don't have to get through all of them. Okay, so here's a simple example. So n equals 1. So we just have one position x and one momentum y. And the Hamiltonian is a half the sum of x squared and y squared. So a half y squared, that's like kinetic energy if the mass is 1. So in physics, kinetic energy is 1/2 times mass times velocity squared. So the 1/2 y squared is the kinetic energy. And then the 1/2 x squared, well, imagine that your mass is on a spring. So x is like how far you are from the origin. And if you're far further from the origin, you have higher energy, and the spring is trying to pull you back. So if you take these equations, which I wrote on the previous page, well, the partial derivative of h with respect to x is, we can just do this. So I was told that I can assume you know what partial derivatives are, but if you don't, or if there's anything else you don't know, go ahead and interrupt. Anyway, so dh dx equals x, and dh dy equals y. So from the equations on the previous page, the time derivative of x equals y, and the time derivative of y equals minus x. And this is you can solve this system of differential equations, typical, oops, I didn't want to do that. The typical solution is x is some constant times sine t, y is some constant times cosine t. The energy, I think I wrote the energy wrong. The energy is c squared over 2. So oops, oh, I didn't want to do that. So you draw a picture. So here's x and y. So here's my mass on a spring. You can think of where it is as being 0. It's not really, this doesn't really work very well if x is too negative. But anyway, think of this as a model of the mass on a spring where it doesn't go, you don't stretch the spring too far. And then if you follow this solution in time, well, I can draw the xy plane, and I can think of the solution to the equation as defining some curve in the xy plane. So at any given time, I'm at some point on this curve, and as time goes on, I move around along this curve, which happens to be a circle. And this is a periodic orbit because you just go around the same circle over and over. Any questions about that so far?
Yeah. What is typically we would like have the spring wouldn't just fluctuate forever. If we have like a dampening thing, what happens? Like if it slowly goes to 0, what does this look like?
Yeah, that's a great question. So that doesn't quite fit into the framework I'm talking about. So I'm talking about a framework where energy is conserved. So like in this framework, if you really wanted to have friction, then I'd have to like have variables for the positions and momentum of like the individual molecules in the spring, which would start moving faster. Like the friction would cause it to heat up and cause those molecules to move faster. There's also there's some other frameworks for sort of dissipative systems where like energy gets lost. Yeah, the framework I'm talking about is assuming conservation of energy. So it's good for like planets in a solar system where there isn't really any friction, but not good for terrestrial things with friction. Other questions?
I'm sorry. I know like basically zero physics, but what do you mean that like energy is conserved? Because like wouldn't friction just make the energy into like
So we're in
'cause,
some
like, energy
ideal
is always
world here
conserved,
where
right?
there's no friction.
Okay, so there's no friction basically.
Yeah.
Got it.
If I want to, I mean, energy is conserved, but if I wanted to allow friction, I would need to keep track of where the energy is going under friction, which I'm not going to do.
Yeah. Okay.
And also,
Um,
y represents momentum here, right?
Sorry? Yes, y is momentum.
Okay, okay. I just wanted to clarify. Thank you.
Okay, great.
Wait, I have a question. Did
Uh-huh.
you derive the differential equations that you were using with the Hamiltonian and X and Y?
No, it's sort of you, you could think of it as an axiom. But basically, I want to write down what are equations of motion. So it's like a mathematical model for how mechanics works, and that's what it is. And so then you can ask, well, why do I write those equations and not some other equations? And then, well, I guess it sort of works well for describing systems as we know it. Like you sort of recover Newton's laws and things.
Just one question. Why do we
Mhm.
specifically use position and momentum? Like, why not like position and something else like velocity or something?
Um, yeah, so that there's an answer to that question, but it's a little subtle. So, like you could take the x's to be any functions you want, um, but then there's some constraint on what the y's can be. They have to be what physicists would call conjugate. I think they call them conjugate variables. Um, it has to do with symplectic geometry, which is actually what I work on. So it kind of hurts me that I can't give you a full answer to this question. But I'm going to need another lecture. But anyway, let me, the technical answer, and I don't expect you to understand what this means, is that um, the whatever variables you use, they have to be obtained from the x's and the y's by a symplectic transformation.
Okay, okay. I'll do more research. Thank you.
Okay. Great. Right. So conservation of energy in this framework, we can just prove it. So you can take any Hamiltonian H, and then you can calculate what is the derivative of H with respect to time. So you have to use the multivariable chain rule. And well, if you've done multivariable calculus, this is a simple exercise. If you haven't, then it's confusing. But anyway, it comes out to 0. So that means, so as you move following the equations of motion, H stays constant. And mathematicians like to think of this geometrically. So we have this 2n dimensional Euclidean space of these x's and y's. And then if we fix the value of the energy, say the energy is equal to 100, well, then we're going to stay on the set where h is equal to 100. And well, what do you expect such a set to look like? Well, if I have some smooth function, and if I have some number, at least, most of the time, the set of points where the level set is what you call it, where the function is equal to that number is a hypersurface. So it's going to be a 2n minus 1 dimensional hypersurface in R2n. For some special values of energy, this hypersurface might have some singularities, but for most values of the energy, it's a smooth hypersurface. In the example we did before, well, this is where n equals 1, and this constant energy hypersurface is just a circle. But for a general Hamiltonian function in 2n dimensional space, it could be some very complicated hypersurface. And then it can give a slightly more precise definition of a periodic orbit. So it's a trajectory x of t. That's kind of, I probably should have used a different letter here. because x is just one of the variables. Let's call it like gamma of t. So you have a solution to the equations of motion, such that for some time capital T, gamma of capital T equals gamma of 0. That's the period. So it just repeats. Now, what's kind of cool is you can show that the Hamiltonian dynamics on some level set y, in some sense, only depends on the hypersurface y. So if you take any other Hamiltonian for which y is a level set, then the equations of motion are going to be almost the same. The only difference is the speed at which you go changes. So in other words, if you start at some point in y, when you evolve according to the equations of motion, you move along some trajectory in y. And for a different h, you're going to move along the same trajectory, just maybe at a different speed. So the periodic orbits in y depend only on y. And these are some sort of loops in y. And you can say it a little more concretely. So there's a vector field v on y. So vector field means at every point in y there's a vector, which is tangent to y. And what this vector is you take a perpendicular vector to y, which is unique up to scaling. And we're in R2n, but I can also think of this as c to the n. So this is tuples of n complex numbers. And then you just multiply every component of this vector by the square root of -1. And that gives you, so that when you do that, you take any vector and multiply it by the square root of -1, you get a perpendicular vector. So if you start with a normal vector to y, you get a tangent vector to y. And a periodic orbit is a loop, which is everywhere tangent to this vector field v. So I drew a little picture here. So here, this blob is supposed to represent the hypersurface. Like think of this as a two-dimensional surface in R3. Well, actually, that's really bad because it has to be even dimensional. Well, whatever. Anyway, so there's a normal vector. You multiply it by square root of -1, you get a tangent vector. At every point in the hypersurface, there's this little red arrow, which is this vector. And then the periodic orbit is a loop where the velocity of the vector of the loop is up to scaling equal to this vector v. Does that make sense? The mathematicians like to think of, instead of like a system of ordinary differential equations, they like to think of it as a vector field. And then the solutions are trajectories of this vector field. Okay. So here's some general questions you can ask. So you're given the hypersurface y, do periodic orbits exist? I don't know. If they do exist, how many are there? What are their properties? Like, what are their periods? And a particular question I'll talk about today, a little later, is what happens to the periodic orbits if you tweak the hypersurface? Like, let's suppose we've got our solar system. Let's suppose our solar system is in some kind of periodic orbit. And then like an extrasolar object flies through the solar system and bumps everything. Well, what's going to happen to your dynamical system after that? These are research questions. Like in general, I should have said this before, because any of you ever taken a class on differential equations? Yeah? No? Well, like the basic differential equations class is a giant lie, because there's a book which says this kind of equation, here's a trick to solve it. This other kind of equation, here's another trick to solve it. You go through the whole book, you've learned a bunch of tricks to solve all sorts of equations. The problem is that's like a measure zero set of all the possible equations. You take a random differential equation, it's completely impossible to solve it explicitly, at least not in terms of any functions you know. So what mathematicians tend to do, well, I mean, if you actually really need to know the answer, like if for like weather forecasting or something, then you can numerically approximate a solution. The mathematicians want to understand stuff, so instead of trying to like find a formula for the solutions, they try to answer these kinds of qualitative questions, like what are the periodic orbits like? So that's what I'm working on here. So now let's actually talk about some hard theorems. So in 1978, Alan Weinstein, who was a retired math professor at Berkeley, proved that if your hypersurface Y is convex, namely it's the boundary of a compact convex set, then there's always at least one periodic orbit. So that means that like, so here's convex. So if this black curve represents Y, then Y is the boundary of some 2n-dimensional region. And if convex here means that if I have any 2 points inside the region, if I draw a straight line between them, it stays inside the region. Okay. And then Paul Rabinowitz proved a generalization to what's called a star-shaped hypersurface. So star-shaped means that if you draw any ray starting at the origin, then it crosses the surface once and it's not tangent. The technical word for not tangent is transverse. So any ray from the origin intersects the hypersurface once transversely. So that's slightly more general than convex. So in that case, also there's at least one periodic orbit. Now, more recently, in a joint work with one of my PhD students at the time, Dan Christopher Gardner, we proved that in the 4-dimensional case, the star-shaped hypersurface actually has at least 2 periodic orbits. And this was proved using some really heavy machinery, like imagine like, nuclear power plants and, robots and all sorts of crazy stuff. So really hard technology. I've been working on trying to sort of simplify the technology for these things, which I'll tell you about a little later.
This might be a random question, but why is 4 dimensions so special in this case? Like,
so it turns out we have more tools available in 4 dimensions than in higher dimensions.
okay.
And why that's true is a deep philosophical question, and I don't
Okay. So it just is.
I don't completely
basically.
know the answer.
Right.
Sorry?
Okay. So it just is special, basically, for like, because it is.
Yeah, I mean, there are some technical things I can say about how 4 dimensions differ from higher dimensions.
Cool.
Have to do with like, I mean, for me, the technical thing is that holomorphic curves in 4 dimensions intersect positively, which I can explain later what that means. Anyway, so for me, like in my own work, they're like various technical things, but if there's any deep reason, I don't know. So we have sort of nice tools in 4 dimensions, which we have some tools in higher dimensions are just not as good.
Could you elaborate a bit on how technology helped with this proof? Like it seems like something like completely theoretical.
Well, by technology, I mean mathematical technology. So I mean like you have to cite, various 800-page books and 500-page papers and stuff. So I mean that's what a lot of what mathematicians do. You could think of it as like engineering, but for math. So you like develop these mathematical theories, and ideally with the goal of solving problems like this. Other questions?
Uh, I didn't really get what a star-shaped hypersurface is.
A star-shaped hypersurface. So hypersurface such that if you draw any ray starting at the origin. So here I've drawn a ray, which is red, that it intersects the hypersurface exactly once, transversely.
Yeah, so how do you do that in 4 dimensions?
Well, it's the same thing. I just can't draw a picture. So I drew a 2-dimensional picture.
Yeah.
So there's like, in 4 dimensions, there's a 3-dimensional space of rays. So they're parameterized by the 3-dimensional sphere. And so every point on the 3-dimensional sphere, there's a ray. It's the given, it starts at the origin, it goes to that point in the sphere, and it keeps going. And I want that ray to intersect my hypersurface exactly once.
All right, thanks.
Like I could draw a picture of something that's not star-shaped. That'd be like, oops. This would fail to be star-shaped because this ray intersects it 3 times, and that's not allowed. Okay.
I have one question.
Mhm.
So like all these theorems like that you have just stated, like all these periodic orbital things on hypersurfaces, why were they proven like so relatively late? I mean, like Hamiltonian mechanics was established like 200 years ago.
Well, the proofs are hard. You can find easier proofs. That'd be awesome.
Okay.
This stuff is hard.
Like were these
It's kind
questions not asked before, or
like I think Poincaré asked some questions along these lines at the end of the 19th century, but didn't have a whole
okay,
lot of tools to answer them.
okay, okay.
Yeah, so that it's a little. The other weird thing about math is that there's some questions which are simple to ask. Actually, often like the questions that are easiest to ask are the hardest to answer. Like the simpler the question, like, all right, well, I don't have any tools, so what am I supposed to do? So you have to build up some tools. So yeah, if you look at research papers, a lot of it is just building up tools for stuff. Okay, great. Now, so I guess I should, yeah. So we proved that a star-shaped hypersurface in R4 has at least 2 periodic orbits. So you could say, well, maybe I should have assigned the next graduate student to prove that there are at least 3 periodic orbits. But that is not true. So I can give you a quick example. So you take a irrational ellipsoid in R4, that's a hypersurface, then it has exactly 2 periodic orbits. So to define the irrational ellipsoid, you pick two real numbers, positive real numbers, A and B. You assume that A over B is irrational. You define the ellipsoid by this equation. So the sum of the squares of the coordinates with some factors is equal to 1. That's an ellipsoid. It's an example of a convex hypersurface, in a particular star-shaped one. And when you work out the equations, well, so instead of using the variables xi and yi, I can use polar coordinates. So r1 is the distance of x1, y1 to the origin, and theta1 is the angle of x1, y1 to the origin. So r1 and theta1 are the polar coordinates corresponding to x1 and y1. And then in polar coordinates, you find that the r1 and r2 are constant, while theta1 and theta2 are increasing at particular speeds. So theta1 is increasing at speed 2 pi over a, and theta2 is increasing at speed 2 pi over b. So this means that if one of the radial coordinates is 0, then you have a periodic orbit. So then the other radius is constant, and that theta is just increasing at some speed until you come back where you started. So the orbit where R2 equals 0, it is period A, because theta 1 is increasing at speed 2 pi over a. So if you go for time a, then you've increased by 2 pi and you're back where you started. And likewise, there's a periodic orbit where r1 equals 0 and it is period b. And there are no other periodic orbits, because if you start at a point where both r1 and r2 are non-zero, then the speeds at which theta 1 and theta 2 are increasing have an irrational ratio, which means like if you were going to come back where you started, then you'd have to go for some time where theta 1 and theta 2 both increase by integer multiples of 2 pi. But that's not possible because A over B is irrational. And physically, this is a pair of simple harmonic oscillators which are vibrating with different frequencies and not interacting. My example before was just a single harmonic oscillator. This is one of the very few examples which is simple enough that I can actually solve the PDE. Okay. Usually, actually, there are infinitely many periodic orbits. So one theorem I can state that there's sort of more general versions of these, but a version that's simple to state is that for any star-shaped hypersurface in R4, there are either two or infinitely many periodic orbits. So there are at least two. If there's a third one, then there have to be infinitely many. And we can also give some characterization of the case where there are exactly two periodic orbits. They're not quite irrational ellipsoids, but they have sort of all the same numerical invariance. And then K. Irier proved a really remarkable theorem. He proved that for a generic star-shaped hypersurface, the set of periodic orbits is dense. So dense means that for any point in Y, you can take any small neighborhood of that point, and there has to be a periodic orbit going through that neighborhood. So, like if you drew the periodic orbits with ink on Y, then it would look black. Well, if you're using black ink anyway. And generic means it's almost always true in some technical sense. So if I take a random hypersurface, then the probability 1 is true. Of course, there are exceptions like the ellipsoid that we just saw.
Wait, but like, how would you define a measure space on the set of all hypersurfaces? That sounds really crazy.
So we don't actually do that. So what generic really means is it's an accountable intersection of open dense sets in the C infinity topology.
Oh, okay.
And so in particular, the concrete thing you can say is that if I take my hypersurface, I can perturb it by a perturbation which is arbitrarily small with respect to an arbitrary number of derivatives
and still get like one of the nice hypersurfaces.
Right. Okay. Well, okay. I'll explain this picture in a second. And the key to proving his generic density theorem is it's what's called a strong closing lemma. And what does it say? Because I have a star-shaped hypersurface, I have a non-empty open set U. So U is like the set that I want to have a periodic orbit going through. And now we're going to perturb the hypersurface so that nothing changes outside of U. But inside U, we are sort of like there's like a little bubble forming, and the hypersurface is expanding outward. So it looks like the did not draw a good picture of this. Actually, I don't think I drew a picture of it at all. So, oh no, here it is. So like I start with Y, this red area is U, and then it's sort of bubbling out inside of U. So that's the kind of perturbation I'm going to do.
has there been any work done for exploring stability and instability for periodic orbits?
Yeah, so that's a slightly different topic. I can come back to that a little later.
And
So for now,
yeah. I have another question that the number we got two or infinity in a star shape hypersurface R4 in the proof is the number two does the number two arise because of 4, or like if for RD would that number change?
so the number two, I'll show you a little later where the number two comes from. We'll see that. Um, and then, yeah, there's a conjecture that in R2n, the hypersurface will have at least n periodic orbits. So that's a famous conjecture, but it's only known in the two in n equals 2. Right. What was his previous picture? I don't know what the picture was for. Okay, anyway, so to complete the statement of this strong closing lemma, it says if you do this kind of perturbation, then for some time t, so here t now, that's not the time in the periodic orbit, that's the time in the perturbation. So I could have a one parameter family of these hypersurfaces. So for some t, there is a periodic orbit intersecting you. So you take y, it starts bubbling out inside you, and at some time t, ping, the periodic orbit is going to appear going through you. And this actually implies that this will happen for arbitrarily small times, because I could really slow down the bubbling up of the surface. And the theorem says that an orbit will appear for some time from 0 to 1. This is actually an amazing statement. So there was a previous closing lemma from the 1960s by Pugh, who was also a professor at Berkeley. So roughly speaking, it says that if you, here's the picture. It says if I have a trajectory which starts in you and comes back to you but doesn't quite close up, then I can perturb the vector field so that the trajectory actually does close up. And the perturbation has to be small. And well, what does small mean? So for Pugh, small means that the perturbation in its first derivatives are small. So, and this is actually very delicate. So in Pugh's theorem, he has to very delicately perturb the vector field so that this orbit will close up. Like it's not hard to prove that you can do this with a C0 small perturbation, but a C1 small perturbation is hard. And then to get it to be small with respect to more derivatives, that was science fiction for decades. And it's one of Smale's problems in his list of math problems for the 21st century. Okay,
So
but
like
in Irias,
is Pugh's theorem, does it follow from Erie's theorem, or are they?
he proves a slightly different statement, but it's in a slightly more general context.
Okay.
But Urias theorem could prove some version of Pugh's theorem.
Okay.
Yeah. Anyway, Urias statement is remarkable because it says you can do anything to y as long as it's sort of bulging out. You don't have to take any care whatsoever, and periodic orbits will appear. It's almost like periodic orbits are like weeds. Like it's really hard to get rid of them, actually. And so this perturbation can be C infinity small. Like you can have all the derivatives of this perturbation of y as small as you want. Um, and
Could you like explain how Erie's theorem actually gives rise to all these closed orbits?
right. Okay. So Erie, like the previous theorem I said, is that generically the periodic orbits are dense. And this theorem just says I can make a perturbation to produce orbits through one open set. So imagine you sort of cover Y by like a bunch of open sets of volume one, and you only need finitely many of them. And then I cover Y by some more open sets of volume a half, and some more open sets of volume a quarter, and some more open sets of volume an eighth. And eventually I'm going to have some countable collection of open sets um, where every point in Y is in one of these sets of arbitrarily small size. So basically you apply the strong closing lemma countably many times to get the dense periodic orbits. That's the rough idea.
Okay, okay.
What
So the
does it
hard
mean
part
by
is
what does it mean by YT agrees with Y?
um, it means that you're not changing it outside of U. So U is some subset of Y. I'm changing Y. I'm changing the part of Y that's in U and leaving the rest of Y alone.
Oh, okay.
So I should prove at least one thing in talk, I think. So I can actually explain, if you're willing to accept a bunch of things on faith, I can tell you the proof of the Urias strong closing lemma. Would you like to see it? Okay. So let's use this in technology, which I invented, which is called the ECH spectrum. So what is the ECH spectrum? So for any star-shaped hypersurface in R4, it's a bunch of real numbers. The C0 is always equal to 0. C1 is positive, and then they're non-decreasing, and they're all finite. They have an infinite series of real numbers. The definition, well, I actually do have a slide on it, but I don't think I have enough time to explain it. But anyway, let's just take it on faith that these numbers exist. And then they have three key properties, and these are all you need to know to prove Fourier's closing lemma. The first property is that each of these numbers is a total period of some finite set of periodic orbits. Now, the period is, the way I explained it before, the period is not really defined because it depends on the Hamiltonian, but there's some sort of nice way to normalize it, so there actually is a well-defined period. And if you deform the hypersurface, and CK varies continuously. And finally, this is the deep one. It's what's called a Weyl law. It says if X is the region bounded by Y, then the limit as K goes to infinity of CK squared over K is equal to 4 times the volume of X. So this is a very non-trivial fact. Like each of these CKs is a total period of some set of orbits. And yet this theorem is saying that out of those numbers, you somehow recover the volume of X. And this exponent 2, this is, that 2 is where the two periodic orbits come from. When I say there are always at least two periodic orbits. I can explain later if there's time. Anyway, so let's suppose you go to the store and you buy a box of spectral invariants. It says on the box, here are the features of this box, here of these invariants. This total period, continuous, the Weyl law. Then you can use that box of invariants to prove Fourier's closing lemma. And here's the proof. I can do it in one page. So we're trying to prove that as I push out the hypersurface along the set U, a periodic orbit will appear through U. So let's suppose to get a contradiction that doesn't happen. So for all t, there's never a hypersurface intersecting. There's never a periodic orbit intersecting you. So then the periodic orbits and their periods don't change because by hypothesis, periodic orbits never intersect you. And we were assuming before that we're not changing the hypersurface outside of you. So the periodic orbits are staying exactly the same. Now, we also have the property that CK is a continuous function, and its value is some finite linear combination of periods of orbits, or some finite sum of them. And it follows that it doesn't depend on t. You need a little argument there. You need to argue that the set of possible values of CK is a measure zero set. But in that case, a continuous function to a measure zero set is to be locally constant. So CK is not changing. On the other hand, we have this Weyl law, which says that I can recover the volume of X as a limit of the CKs. And the volume of X is increasing because I assume that I'm pushing the hypersurface out. So the volume is increasing, and that's a contradiction. So in this Weyl law, the left side does not depend on t, and the right-hand side is an increasing function of t. Contradiction. Isn't that amazing? So this is the kind of thing when you see this paper, you're like, damn, I should have thought of that. But I didn't. So Urié is very clever. This is a beautiful argument of his. His whole paper, like including all the technical details, is like 5 pages. All right. Any questions about that argument? So, well, this might make you think, oh, research math is easy. You just like have a clever idea and write a page and you're done. But usually it's not like that. Usually you toil in agony writing hundreds of pages of technical stuff, and every now and then you produce a little bit of something interesting. What's also deceptive is things get simplified over time. So like if you read a math book, like pick up a book on like, I don't know, real analysis, everything's all like clear and simple and well organized, but there is some tortuous path by which researchers, discovered things and simplified and rethought things until they got them to that point. So like all the technology that goes into the proof, these CKs, that's actually quite complicated, although I've been working on simplifying it. Okay. So
like, does this argument like use homotopy theory?
it does not use homotopy theory.
Okay.
I mean, well, not really. I mean, there's homology of a chain complex somewhere, but there isn't like homotopy groups of things.
Okay. Okay.
There is a lot of partial differential equations in here. So there are pseudo-holomorphic curves, which you can think of as being kind of like minimal surfaces. But then there's the Seiberg-Witten equations, which come from mathematical physics. And I can write down the equations, but I can't tell you where they came from. Right. So I don't think it's that important for me to tell you about my own research, but since I have 10 minutes left, I can try to state a theorem I proved. And so this is about quantitative closing lemmas. So Urié's closing lemma says that if I deform the hypersurface, I'll make a periodic orbit. But it doesn't give me any upper bound on the period. So the period could be super, super long. You could say, well, what if I want to make a period with some bound? What if I want to make an orbit with some bound on the period? Let's say the period's at most L. Well, how much do I have to deform y? Like you imagine if I only deform y a little bit, then maybe it's going to take a really long time for the periodic orbit to appear. Like you can imagine, like in U, like you start at some point in U, eventually you can prove that because of the flow is volume preserving. I didn't get into that, but you can show that if you start in U, eventually, or at least there's going to be some trajectory which starts in U and comes back to U, but it might not come back very close to where it started. Um, and well, if the trajectory is not very long, then you're probably going to have to push it a fair bit to make it close up. But if the trajectory is really long, then maybe you don't have to push it as much. So anyway, I can prove a theorem which says that in some sense, the amount that you have to form the hypersurface to make an orbiting period at most L is on the order of 1 over L. There's a precise statement, which I won't have time to completely give. But there's some notion of the width of the deformation. And so like when I puff up the hypersurface, there's some region in between the new hypersurface and the old hypersurface. And the width is roughly the square root of the volume of the region. The actual definition is more complicated. And now I have a slightly confusing definition. So this is what I call close L. So basically, close L says, how much do I have to deform the hypersurface to be guaranteed to produce an orbited period at most L? The precise definition is like a confusing string of quantifiers, but that's what it means. So if close L is equal to 17, that means if I do a deformation of the hypersurface of width at least 17, then I'm guaranteed to produce a periodic orbit of period at most L. So if close L is finite, then that means I have a quantitative closing limit. It means I've given some bound on how much I have to deform the hypersurface to get a periodic orbit of a period at most L. If close L is infinite, then it sort of doesn't tell me anything. So if I want to prove a non-trivial theorem, I've got to prove that this close L is finite. In fact, close L is infinite if L is less than the minimum period of any periodic orbit. But as L gets bigger, close L becomes finite, and it's decreasing. It can even be 0. Like if you have a rational ellipsoid, then every point is already on a periodic orbit, a period less than or equal to L for some L, and then close L is 0, because you don't have to deform it at all. So here's a theorem. And this is in my paper, which if you want to see the actual paper, that's the archive coordinates of the paper. So it says if Y is a star-shaped hypersurface, then the lim sup of L times close L is less than or equal to 2 times the volume of X. So this means, roughly speaking, that close L is less than or equal to 2 times the volume divided by L, plus some error, and that error goes to 0 as L goes to infinity. So basically close L is less than or equal to 2 times the volume divided by L. It could be much less, but anyway, that's a sort of asymptotic upper bound on close L. So close L is on the order of 1 over L when L is large. That's the statement. And the proof is a refinement of Fourier's argument, which I won't have time to explain. And in some cases, you can actually compute this close L exactly. So yeah, that's a That's a theorem. Any questions about what that says? Right. Well, I have some slides talking about the spectral invariance. I think that's maybe I've done enough technical stuff, and I should just stop. And you can ask me any questions you want, and I can explain more things as you like.
I have a general question about the term orbit here. Is there a way
Yeah.
in which these orbits are like orbits of a group action?
Yes. So there's an action. If you think of the set of real numbers as a group with addition, then that group acts on Y. So the action is if you act by some real number, it means you start at a point and you follow the flow of the vector field for that much time. And then the orbits are actually orbits of the group action. If you start at a random point, usually it's not going to be a periodic orbit, so it'll just sort of go on forever without ever coming back. So periodic orbit is one of these orbits where, well, in the language of group theory, it has some non-trivial stabilizer. There's some non-zero points where go back where you started.
Then could we do like, I don't know, some sort of, I don't know dynamics very well, but like, could we do some sort of dynamics using like an arbitrary group instead of the real numbers?
Yes, so there's a lot of research on that sort of thing. There's a subject called homogeneous dynamics. So they have actions by various Lie groups on various spaces and study them. And it gets sort of more algebraic. Usually, like they're starting with some sort of nice group actions which they can write down and then studying cool properties of them.
Wait, but like I understand that we care about like these group actions and real numbers because physics, right? So like why would you care about random for like other nice groups? Why do you care about the actions?
Um, well, I guess it's more for mathematical reasons, but there are all sorts of group actions that come up in mathematics as symmetries of various spaces,
Yeah,
and
yeah.
you'd like to understand what are these group actions doing.
Okay, no, but like for like this stuff, like the orbits, this thingy. Like I'm not sure I'm not sure what it's called. Sorry. Like yeah, like I mean I know like group actions are important, but like why but what's like the thing you just did with them? Why what reasons do we have to do them more to other groups?
Um, well, I don't. The things that I'm talking about in particular, I don't know how to make sense of them for other groups, with the exception of like you do like finite groups, like um, um, instead of having a continuous flow, you could just move in discrete time intervals. That's another way of modeling physical systems. Is you sort of iterate some function from the space to itself. So that I've studied things like this for groups of dimension bigger than one. I haven't really worked on that topic.
You mentioned that you use like homology of chain complexes. I think to define the like spectrum, the CKs. What
Yes.
particular like homology theory are we using there? Because like, is it like singular? Is it like which is it day wrong? I don't know.
So there's a theory called embedded contact homology, which is kind of my flagship product, so to speak. So it's not like a homology of a topological space in the sense of an algebraic topology book, uh, but it's a homology theory which is supposed to detect periodic orbits. So there's a chain complex, and a generator of this chain complex is, roughly speaking, a finite set of periodic orbits. And then there's a differential. The differential involves holomorphic curves, so I didn't get into that. But the differential, roughly speaking, keeps track of when there are holomorphic curves with boundary on two different sets of periodic orbits. So the differential is some kind of count of certain holomorphic curves. And then that theory has various properties, and you can extract the CK out of it.
So when you say holomorphic in like higher dimensions, what do you mean?
Okay, well, so I have some blank pages I can write on. I did have a slide of open questions. I want to show you that in a minute, but first let me answer your question. So the holomorphic curve, I want this to be black. There we go. So you have a Riemann surface. I think this is maybe beyond the prerequisites for this talk. So if you don't understand this, don't worry about it. I'll just stay for a minute. So this is a Riemann surface. So it's a two-dimensional surface, and little j takes a tangent vector and multiplies it by I. And then you have some two n-dimensional manifold, an almost complex structure, capital J. And a holomorphic curve is a map U, which, well, it satisfies the partial differential equation, du composed with little j equals big J composed with du. So if you've done complex analysis, like when you look at holomorphic functions on the complex plane, holomorphic basically means the derivative commutes with multiplication by I. And then this is a version of this where instead of mapping the complex plane to itself, you're mapping some Riemann surface to some other manifold with an almost complex structure on it.
And so like J does the work similar to what I does in complex analysis?
Exactly. So you can think of J as multiplication by I.
Okay. And what are these derivatives like du? Like
So if you have any smooth map between two manifolds, it has a derivative du. So locally, you write both spaces in terms of local coordinates, and then du is the matrix of partial derivatives.
okay.
All right. Since I forgot to list my open questions, if you don't mind, I want to squeeze these in. I should have done this before. So as I mentioned before, there's an old conjecture that every star-shaped hypersurface in R2n has at least n periodic orbits. And there are a whole bunch of partial results on this. So Yiming Long and students have proved many partial results, but the general conjecture is open. It's not even in 6 dimensions, it's not known that every star-shaped hypersurface has more than one periodic orbit. You could then ask, if there are more than n periodic orbits, do there have to be infinitely many? You could say, is there binaric density, like we discussed today, for hypersurfaces in R2n with n bigger than 2? But that's been proved for a few examples, but it's mostly an open question. You can ask, what is the minimum period of a periodic orbit? So there's a famous conjecture of Viterbo, which says that the minimum period is given in terms of the volume of X. I neglected to update the slides because a few months after I made the slides, this conjecture was disproved in this stunning development. So this is false. That was proved by I.M. Kislev. And Ostrover. That's two people, one of whom has a hyphenated name. You can look up their paper. It's actually also a short, simple paper. With one of my students, we spent a bunch of time searching for counterexamples by computer. We didn't find any, but I guess we didn't try hard enough.
Wait, like, did you just find a counterexample, or like they prove?
Yeah, they found an explicit counterexample.
That's crazy. Wait, but like, how false is it for like a counterexample? Like, is it like a bit false or like very, very false? Like how far off is it?
Off by a little bit. I think the minimum period is like 1.04 times the conjectured upper bound.
Wow,
So it's like 4% off or something.
that's crazy. So it could be true. If so, something similar could be true, I guess. But like,
I mean, it's known that there's some upper bound. Like, so this is known to be true up to some constant. The conjecture is that the constant is
okay.
1. That's been disproved. It's reasonable to conjecture that in the 4-dimensional case, it's true up to a factor of 2.
Okay,
but
that's cool.
Yeah. You can also ask, like, what about the growth rate of the number of periods? Orbits of period less than or equal to L. What about periodic orbits of more general vector fields? That's a very subtle question. Like, you can make vector fields that have no periodic orbits. So the question is, what exactly do you need to know about a vector field to know that it has periodic orbits? I don't know. Okay, so those are my open questions. So if you have more questions from the audience.
Before, when you're talking about like a series of C's, you were saying you're like summing up some kind of quantity, but it wasn't exactly length. Like, what kind of quantity were you summing up? Was it energy or something else?
Well, it's the period for a particular normalization of the Hamiltonian vector field.
On a normalization, okay.
So the Hamiltonian, you fix a hypersurface Y, the Hamiltonian vector field up to scaling depends on the Hamiltonian, but there's some preferred scaling, and it's a period with respect to that. If you want a slick definition, I don't know if you know all this terminology, but you have your periodic orbit, which is like a loop. You take a disk in R2n, whose boundary is that loop, and then you take the symplectic area of that disk.
Will you be sharing the slides with us?
Yeah, I can email the slides to Simon and he can share them with you.
Okay.
And if you like, if any of you tries to sort of dig into this topic more deeply and you have questions, you can email me.
Okay.
Well,
Okay.
I'll try to answer if the question's not too complicated.
I really liked your talk.
Thank you.
Okay, are there any other questions? Okay, well, if there are no other questions, then thank you for a great talk. And now we'll move on to the next section of the class.